Hello everyone. Today I am going to explain how to convert Cartesian integral into polar. So in today's lecture I am going to explain how to convert Cartesian integral into polar. So you are given a double integral of function of two variables over the region R. We have to convert this double integral into polar. So the procedure is we substitute x to be r cos theta, y to be r sin theta, and convert the function f of xy into a function with variables r and theta by substituting x to be r cos theta and y to be r sin theta. Then we sketch the region and we will find out the limits for r and theta. So we have to convert this dA, where dA is dx into dy or dy into dx, whatever. We have to convert this into dr d theta. Basically this area in Cartesian is replaced with r times dr d theta in polar. Now see how. So in Cartesian we are given any region. We split this region into small meshes, means small rectangles. We find out the area of this small rectangle, let it be dx, this be dy. Then dA is nothing, dx into dy, which is the area of small rectangle. Then we multiply this dA with the value of the function at this point. Then this will become this f of xy, which is z. This will become the height. When you multiply height with the area, you get the volume. And when you add all these volumes, you will get the total volume, which is the double integral of the function over the region R is the volume. Now we have to convert this into polar. So we have to consider this origin as a pole, and we have to consider an initial ray passes through this. And we have to observe what is the value of r and what is the value of theta. So now if you pass an initial ray in the region, now the small rectangle will convert it into a small sector portion. So dx dy will be replaced by this small portion. So we have to find out the area of this small portion. Now just see, let's suppose this is your initial ray. We have to find the area of this small portion. Let this angle is d theta and this distance is dr. So we have to find out the area of this small portion. For this we suppose that let there be any point in the mid of this having the coordinates r and theta. Means this distance, this angle is theta and this distance is r. Right? So this distance is r over this line. Now just see, what will be the radius of this large one sector? Since this point is at the mid, this radius is r and this is dr. So dr by 2 we will add in r, we will get the radius of this large sector. So the radius of the large sector is r plus dr by 2. So if we have the radius, we have the angle, we can find out the area of the large sector. So what will be the area of large sector? The area of large sector will be r plus dr by 2 whole square into the half of the angle, which is d theta by 2. So this is the area of the large sector. Similarly, find out the area of the small sector. Now if this radius is r and this is dr by 2, then the radius of small sector will be, the radius of small sector, it will be r minus dr by 2. So what is the area of small sector? The area of small sector will be radius square into half of the angle. So if we subtract the area of large sector and area of small sector, we get the area of this small portion. So what is the area of this small portion? This will be area of the large sector minus the area of small sector. So this is d theta by 2 common, r plus dr by 2 whole square minus r minus dr by 2 whole square. So when you open this, you get this is d theta by 2 into 4 times r dr by 2. So this is r dr d theta. So the area of the small portion will be replaced by will be r into dr by d theta. So that means dA will be replaced by r times dr d theta. So now just see what will the form. So if you are given a double integral in Cartesian over some region, then you can write its equivalent integral in polar by putting x to be r cos theta and y to be r sin theta and converting the function f of x y into f r theta. Then you can replace dA, which is dx into dy, by r times dr d theta. Now you write down the limits for r and then the limits for theta. So for this you have to sketch the region R. So you sketch the region R. Consider this origin as pole, take an initial ray in that region and see from where to where your R is varying and what is the angle. That is the limit for theta. So this is a procedure to convert Cartesian integral into polar. If you are given a Cartesian integral, you can write down its equivalent polar integral by substituting x to be r cos theta and y to be r sin theta in a function, and by replacing dx into dy by r times dr d theta, then find the limits of r and theta in the given region. Now just see with the help of an example. Let's suppose you have to write down an equivalent integral of this function over the region R in polar, where this region R is the semicircle. It's a semicircle bounded by the line y is equal to 0 and the circle x is equal to square root of 1 minus y square. Find out the write down the equivalent integral in polar, where this r is the semicircular region. It's a semicircular region bounded by the line y is equal to 0 and y is equal to 0 line means what? X-axis. So it is bounded by the line x-axis and the curve y is equal to 1 minus square root of 1 minus x square. So first of all you sketch the region. Now what is the region? This is your x-axis, this is your y-axis. So y is equal to 0 line is this one, and y is equal to square root of 1 minus x square, a semicircle, this one. The coordinates are minus 1 1, right? This is 1. So now you have to write down its equivalent integral. You substitute x to be r cos theta and y to be r sin theta, and you can convert this function in r theta. Replace dx dy with r times dr d theta. Now you write down the limits for r. For this you consider this as pole. Take an initial ray passes through this region. Our r is always varying from 0 to this curve. Here the value of r is 1. So the limits for r will be 0 to 1, and theta, it is moving from here to here. Here theta is 0, then 90 degree, then pi. So theta is 0 to pi. So in this way you can write down an equivalent integral of Cartesian in polar. Now just see with the help of one more example. Change the Cartesian integral into its equivalent. Polar integral and then evaluate it. So the question is 0 to 2, 0 to square root of 4 minus y square, x square plus y dx into dy. So first of all we sketch the region. Here the limits for x is x going from 0 to this. So this is a circle with radius 2. Our x is varying from 0, here x is 0, to this circle portion. So this is r is equal to 2, because your x is square root of 4 minus y square. It means squaring both sides, x square plus y square is equal to 4. It means r square is equal to 4, or you can say r is equal to 2. R may be minus 2, but that is denoted by the backward distance. Now the limits for y is 0 to 2. So the minimum value of y is 0 and the max value of y is 2. Right? So this is the portion. So this is a circle in the first quadrant only, having center as 0 0 and radius 2. Now you consider this as pole. Take an initial ray passes through this region. Our r is always varying from 0 to this. Here the value of r is 2. So the limits for r will be 0 to 2. Convert this into r theta. So when you substitute x to be r cos theta and y to be r sin theta, this is a r square. And this is replaced with r times dr d theta. The limits of r is 0 to 2 and the angle is 0 to pi by 2. So this is an equivalent integral in polar. Now we can evaluate it. We can club this r, this is r cube. When you integrate this, you get this is r4 by 4. Substitute the limits. You get this is 2 to the power 4 by 4, which is 2 square 4 into d theta. So when you integrate with respect to theta, you get theta, and when you substitute the limits, you get pi by 2. So this is 2 into pi. So this is the value of this double integral, right? So in this question, we have to first change the Cartesian integral into its equivalent polar. So we convert this integral into polar by substituting x to be r cos theta, y to be r sin theta, and by replacing dx into dy with r and dr d theta. By writing the limits for r first and then for theta, evaluate this, right? Now just see one more example. Now just see what will be the area in polar. Now just see in Cartesian, what is the area? It is the double integral of the function 1 by considering function to be 1 over the region R. So since we know that in polar this dy into dx or dx into dy, this will be replaced with r times dr d theta, and we have to consider function to be 1. So this is an equivalent integral in polar. So the area in polar integral form will be this one. So if the next question is find the area of the region common to the interiors of the cardioids, r is equal to 1 plus cos theta and r is equal to 1 minus cos theta. So you have to find the area of the region which is common to the interiors of the cardioids. R is equal to 1 plus cos theta and r is equal to 1 minus cos theta. First of all, we draw these regions. We draw the graph of these polar curves, right, by writing its all symmetries. Since we know that these two are symmetrical about x-axis only, so we have to consider theta to be 0 to pi, and we can find out the values of r and we can draw the graph. R is equal to 1 plus cos theta. This will be a cardioid having this shape, and r is equal to 1 minus cos theta. It's a cardioid having this shape. Right? Now what is the common region? Common interior to both the cardioid is this one. So we have to find out the area of this region. Right? So we consider this as a pole. We pass an initial ray. The area will be given by r times dr d theta. Now we have to write down the limits for r. So when you take an initial ray, passes through a region in the increasing direction in the region, so it varying from 0 to this curve. Here the value of r is 1 minus cos theta, and the theta is 0 to pi by 2. Now this is the area of the first portion, this small first portion, but we have to find out the area of this 4 so we can take 4 times. So this is the area of the region which is common to the interior of the cardioid. R is equal to 1 plus cos theta and r is equal to 1 minus cos theta. Now you just simplify this. First find out this integral by integrating with respect to r, and after substituting the limits, then integrate with respect to theta and substitute the limits. So this is the area of the common region. Now just see one more example. Find the area of the region that lies inside the cardioid r is equal to 1 plus cos theta, and outside the circle r is equal to 1. So first of all we sketch the region r is equal to 1 plus cos theta and r is equal to 1. Since this is symmetrical to x-axis only, the graph of this is this one. So this is the graph of r is equal to 1 plus cos theta. Now we have to draw the graph of a circle. So this is 1. Wait a minute, we can take a different color. So this is the circle. Oh, sorry. We have to draw a circle with radius 1. So this is wrong one. Once again, see, first we draw the graph of r is equal to 1 plus cos theta. Now we will draw the graph of circle with radius 1. So we have to find out the area of the region which lies inside the cardioid and outside the circle. So this is the portion. So this is the pole. If we consider initial ray in this region, it always varying from here to here. Here the value of r is 1 and here the value of r is 1 plus cos theta. So the area will be r times dr d theta, and the limits for r is going from 1 to 1 plus cos theta. And the angle, it moves from, in this region, angle is going from minus pi by 2 to plus pi by 2 from here to here. So the value of theta is minus pi by 2 to plus pi by 2. First evaluate this integral, substitute the limits, and then evaluate the other integral with respect to theta. Now one more question. Find the area of the region cut from the first quadrant by the cardioid r is equal to 1 plus sine theta. First of all we sketch this region. This is symmetrical to y-axis. This is this shape. Now we have to find out the area of that region which is cut by the first quadrant. So the region which is cut by the first quadrant is this one. Right? So we consider this as pole. We pass initial ray. Our r is always varying from 0 to this. Here the value of r is 1 plus sine theta. So the limits for r will be varying from 0 to 1 plus sine theta. In the first quadrant, theta is 0 to pi by 2. Again, first evaluate this integral, substitute the limits, and then with the respect to theta. Now just see one more example. Find the area of the region enclosed by one leaf of rose r is equal to 12 cos 3 theta. So first of all sketch this region. Now just see, r is equal to 12 cos 3 theta. It is symmetrical to x-axis by a point r minus theta. When you substitute this, so you will get left hand side is same as that right hand side. So this point satisfying the graph. So this implies graph is symmetrical about x-axis. Now you need to check whether it is symmetrical to y or not. So for this, if any point P satisfying the graph, we have to show that either P dash satisfying the graph or not. What are the coordinates of P dash? It is r comma pi minus theta or minus r comma minus theta. This not satisfied, this also not satisfied. So the graph is not symmetrical about y-axis. So clearly it is not symmetrical about pole. So we have to consider theta varying from 0 to pi. So when we put theta to be 0, then find its value at 15 degree, then 30 degree, then 45, 60, 90, 120, 180. The value of r will be 12 into 1, then 12 into cos of 45, which is 1 by square root of 2, then 12 into cos of 90, which is 0, then 12 into cos of 3 5s are 15, 3 4s are 12, and 13, 135 degree, then 12 into cos of 180, then 12 into cos of 270, 12 into cos of 360, so here it is 12, here it is 12 into square root of 6 into square root of 2, here it is 0. Now here the value of cos 135, it lies in the second quadrant, it should be negative 1, right? It's minus 12. 270, it's lie in the third quadrant, it is also negative 1. So now just see the graph of this. If you consider this as initial, at 0 it is 12, at 15 degree it is 6 into square root of 2, at 30 degree it is 0, so it is a leaf, this one. Now since your graph is symmetrical about x-axis, so this is the complete leaf, right? And when you move angle 135, it is negative, you come back. When you move angle 180, it's minus 12, which is come back, right? And so on. Now since this graph is symmetrical about x-axis, so you get this leaf. So now just see in the question, we have to find the area of the region enclosed by one leaf of the rose, this. So that one leaf is this one, we have to find the area of this. So we consider this as a pole and we have to pass initial ray through this. So our r is always varying from 0 to here the value of r is 12 cos 3 theta, and r theta, it's varying from 0 to this, it is 0 at 30, so 0 to 30 degree, and you make it twice because you have to find the area of this complete one leaf. So this is the value of area. So first you can integrate with respect to r, substitute the limits, and then with respect to theta. So this is the area. Now next is evaluate triple integral. Now triple integral of a function of three independent variables with respect to each variable over some region. It represents the surface density, right? So we have to first integrate with respect to x, substitute the limits of x, then with respect to y, then with respect to z, and substitute all the limits. Now what is the volume? Using triple integral, we consider function to be 1, we get volume. First write the limits for x, then for y, then for z. So in this way we can evaluate the triple integral. So here the limits are already given to us, we have to just evaluate this triple integral. Now see, with the help of an example, evaluate this triple integral x square plus y square plus z square with respect to x, y and z, and the limits of x are 0 to 1, y are 0 to 1, z are 0 to 1. So whenever we integrate with respect to x, we have to treat y and z to be constant. So the integration is x cube by 3 plus x times y square plus z square. Now you substitute the limits. When you put x to be 1, you get 1 by 3. Here it is y square plus z square. Now you integrate with respect to y. So you get this is y by 3 plus y cube by 3 plus zy. So when you put the limit 0 to 1, you get 1 by 3 plus 1 by 3 plus z. Now integrate with respect to z, you get 2 by 3 into z plus z square by, here it is z square, so z cube by 3. Now you substitute the limit 0 to 1, you get 2 by 3 plus 1 by 3, which is 1. So this is the evaluation of triple integral. Whatever the first, you have to integrate with respect to the first variable, then with respect to the second one, then with respect to the third one, and substitute the limits. So this is the evaluation of triple